Now let's look at the situation where we want to integrate a proper rational function r of x over q of x, and the denominator q of x has some repeated irreducible quadratic factors. So these are factors of the form some irreducible quadratic to the power of k. In the partial fractions decomposition, for each one of these repeated irreducible quadratic factors in the denominator q of x, we include k terms, one for each power of this irreducible quadratic factor. The denominator of each of these terms is some unknown linear polynomial. And to integrate terms like this, we might be able to use regular substitution if we're very lucky, or we might have to use a trigonometric substitution after we complete the square in the denominator. Let's have a look at how this works. Let's try to evaluate the integral of x to the 4 plus x squared plus 1 over x times x squared plus 1 squared. And we see here we have one linear factor, which we treat as before, and we have one repeated irreducible quadratic factor, namely x squared plus 1 to the power of 2. For the linear factor x, we include a term in our partial fractions decomposition of the form a over x. And for the repeated irreducible quadratic, we include two terms, one for x squared plus 1 and one for x squared plus 1 squared. And the denominator in both of these cases is an unknown linear polynomial. So our partial fractions decomposition looks like this. And we now must solve for these unknown coefficients. And remember, the trick is always to multiply by the denominator on the left-hand side, the denominator of our original rational function, and then to cancel whatever we can on both sides of this equation. So on the left-hand side, we end up with x to the 4 plus x squared plus 1. And on the right-hand side, in the first term, the x's cancel, and we're left with a times x squared plus 1 squared. And in the middle term on the right-hand side, an x squared plus 1 cancels, and we're left with bx plus c times x squared plus 1. And in the last term, the x squared plus 1 squared cancels, and we're left with x times dx plus e. Now we're left with two polynomials which are equal. And remember, if two polynomials are equal, the coefficients of their powers of x must also be equal. So we expand the right-hand side and gather up the coefficients of the powers of x from x to the 0 to x to the 4. And then comparing coefficients on both sides of this equation, we get that the coefficient of x to the 4 on the left is 1, and on the right it's a plus b, so we get a linear equation in our two unknowns a and b, a plus b equals 1. And likewise, comparing the coefficients of x cubed, we get c equals 0. Comparing the coefficients of x squared, we get 1 on the left and 2a plus b plus d on the right. And comparing the coefficients of x, we get 0 on the left and c plus e on the right. And comparing the constant term, we get a equals 1. Well, now we have two values for a and c straight off the bat. We have a is 1 and c is 0. And if we plug in a equals 1 into the equation a plus b equals 1, we have to have b equals 0. And if we plug in c equals 0 into the equation c plus e equals 0, we must get e equals 0. And then plugging all of this into the equation 2a plus b plus d equals 1, we have d equals negative 1. So substituting these values for a, b, c, d, and e into our original partial fractions decomposition, we see that our rational function is 1 over x minus x over x squared plus 1 squared. And now this is easy enough to integrate. Of course, the integral of the left-hand side equals the integral of the right-hand side, and we can break that up into the integral of 1 over x minus the integral of x over x squared plus 1 squared. And the integral of 1 over x is the natural log of the absolute value of x. And if we make the substitution u equals x squared plus 1 for the integral minus x over x squared plus 1 squared, we get the integral of minus 1/2 over u squared, and this turns out to be 1 over 2u. So our final answer, the integral of our proper rational function, is the natural log of the absolute value of x plus 1 over 2 times x squared plus 1 plus a constant.